Hello all, welcome to today's session on high pass RC circuits. In today's session, we will discuss about first order high pass filter or single stage high pass filter. So we will be discussing about first order high pass filter or single stage high pass filter. The circuit diagram of a high pass RC circuit is as shown in figure. We have basically two components. This is an RC circuit, right? RC circuit. So RC circuit means we have basically two linear elements. One is R, the resistor, and the other one is capacitor C. Okay. Now the input Vi is the input here, is applied across these two terminals. You can see here these two terminals Vi. One is directly given to the capacitor. One terminal is connected to the capacitor terminal. And the output V0 is taken across the resistor R, and let I be the current flowing through this high pass RC circuit. Okay. Now this circuit basically behaves like a filter. So what is a filter? Filter means filter circuits. So filter means a filter will pass a particular set of frequencies and it will block another set of frequencies. Correct? A filter will pass a particular set of frequencies and it will block another range of frequencies or set of frequencies. So the figure shows, the circuit diagram shows a high pass filter. What do you mean by high pass filter? So high pass filter means high pass filter. From the name itself it is clear. High pass filter. High pass filter means it will pass high frequency components and it will block low frequency components, or it will attenuate low frequency components. High pass, right? High pass. High pass, from the name itself it is clear. It will pass, it passes high frequencies. It passes high frequencies and it attenuates or it blocks. Okay, so it's not completely blocking, it's attenuating, right? So it blocks low frequency components. Okay, so in those applications, in those signal processing applications where I need to block low frequency components and I want only high frequency components to pass through the circuit, then I have to design a high pass filter. And the figure shows, in today's session we will discuss about a simple first order high pass RC circuit. Now what happens to this particular, let us see how the circuit behaves like a high pass filter in very simple terms. Okay. Now let us see what happens at high frequencies. Let us start with low frequencies. At low frequencies of Vi, at low frequencies of Vi, of input, what happens at low frequencies of Vi? So what happens at low frequencies of Vi? What happens at low frequencies of Vi? At low frequencies of Vi, you have a capacitor here, right? You have a capacitor here, and the reactance of the capacitor is frequency dependent. Reactance will change depending upon the frequency. And what is the reactance of the capacitor? Xc, reactance of the capacitor. Xc is the reactance of capacitor. Reactance of capacitor. What is Xc? What is the expression for Xc? Xc is 1 by omega c, which is equal to 1 by 2 pi Fc, correct? So Xc, reactance, is 1 by 2 pi Fc. Now what happens to this if F is small? You have frequency component here, right? F. If F is small at low frequency values, what happens? Xc becomes very large. Reactance becomes very large. Reactance of the capacitor becomes very large. Okay, so at low frequency values of Vi, at low frequency values of input, the reactance of the capacitor will be very high. Why the reactance is very high? Because reactance is frequency dependent. Reactance X is equal to 1 by omega C, or it is 1 by 2 pi Fc, right? So what happens is that at low frequency values, since F is small, X is large. So since the reactance is very large, majority of the voltage will drop across the capacitor. You know KVL, Kirchhoff's voltage law. If you apply VI here, that VI will drop across capacitor and resistor. Correct? You have only two elements here. So whatever VI you are applying will drop across capacitor as well as resistor. Now what happens if reactance of capacitor is very large? What happens if reactance of capacitor is very large? If reactance of capacitor is very large, if Xc is large, majority of the input voltage will drop across the capacitor. Majority of input voltage will drop across capacitor. What that means, the drop across the resistor will be small, correct? That means if drop is more in the capacitor side, that implies drop across a resistor is small. Tell me what is drop across a resistor? That is V0. That means V0 is very small. It is approximately equal to 0. It is blocking, right? It blocks. V0 is approximately 0. If you apply low frequencies, V0 is approximately 0. So that means it blocks low frequencies, or it heavily attenuates low frequency components. It will not pass low frequency components to come to the output or to drop across a resistor. Why? Because the reactance of the capacitor is large. Just like this. Let us see what happens at high frequencies. So at high frequencies of input, at high frequencies of Vi, of input, what happens at high frequencies? Just like this. What happens to the reactance of the capacitor value? What happens to reactance Xc? What happens to reactance Xc, which is equal to 1 by 2 pi Fc, right? 1 by 2 pi Fc becomes small, right? Becomes small here as F increases, frequency increases. As frequency increases, Xc decreases. Reactance will be small. So if reactance is small, if Xc is small, that means drop across their capacitor will be small, correct? The voltage drop across C will be small, correct? Why? Because reactance is small. So what happens? Reactance of that is small means majority of the voltage, very less drop across capacitor. So majority of the voltage will drop across resistor, correct? So majority of input voltage will drop across a resistor, correct? Majority of the drop will of the voltage of the input will drop across the resistor, which is nothing but the output. That implies V0 is large. There is no attenuation, right? So almost all Vi you will get at the output. Majority portion of this Vi you will get at the output, correct? So Vi will appear at the output. Means what? It passes high frequencies. That means it passes high frequency components. Okay. So a high pass RC circuit as shown in figure It pass high frequency components and it attenuates low frequency components. Okay, so that's the conclusion. So the conclusion is that an RC circuit like this, if you have a capacitor C and if you take the output across resistor R, if this is V0, if you take V0 across R and if you apply Vi across these two terminals, then such a circuit will attenuate low frequency components. Such a circuit will attenuate low frequency components or low frequencies, okay, low frequency components, and it passes, right? Such circuits will pass high frequency components. It pass high frequency components, right? Such circuits will pass high frequency components. Okay, hence I call it as a high pass filter. Hence I call it as a high pass filter. Now let us see the analysis part. So let us do the analysis of high pass RC circuit. The circuit diagram of the high pass RC circuit is as shown in figure. We have a capacitor, we have a resistor. Let I be the current flowing through this, Vi be the input, V0 be the output, or V0 be the output. So let us analyze this. Let us analyze the frequency response scara of. Let us analyze the frequency response scara of this circuit. So let us analyze the frequency response scara. Let us analyze the frequency response scara, so that we will be able to understand how the circuit will behave with respect to different input frequency values. Okay, so for that, let us start with the expression for V0 output. V0 is equal to, and it is very clear from the circuit diagram, V0 is equal to I into R, correct? So I is the current flowing through this loop, through this path, and R is a resistance value. So V0 is the voltage drop across this R. So V0 is equal to I into R. Very simple, right? Let it be equation number 1. Similarly, what is Vi? What is Vi? Vi here is equal to, Vi is the drop across capacitor plus drop across resistor, right? That's based on KVL. Vi will drop across capacitor as well as resistor. Now, what is that? I into impedance of capacitor. What is impedance of capacitor? 1 by j omega C plus resistance value R. Okay, so I into 1 by j omega C plus R. That is equation number 2. Now let us divide equation number 1 by equation number 2. So V0 by Vi, equation number 1 by equation number 2 is equal to I into R divided by I into 1 by j omega C plus R. And here the I term will cancel. I and I will cancel. So I and I will cancel. And what I am getting is, this is equal to R divided by R plus 1 by j omega C. So V0 by Vi is equal to R divided by R plus 1 by j omega C. Now let us take R outside. So this is equal to, from the denominator, let us take R outside. So this is equal to R divided by R into 1 plus 1 by j omega RC. So I will take R outside, so that R term will cancel. So R and R will cancel. And what I am getting is V0 by Vi is equal to 1 divided by, so V0 by Vi is equal to 1 divided by 1 plus 1 by j omega RC. Or this can be rewritten as, this is equal to, this can be rewritten as, this is equal to 1 divided by 1 minus j into 1 by omega RC. Or this is equal to 1 divided by 1 minus j into 1 by 2 pi f RC. Why? Because omega is equal to 2 pi f. Okay, so the expression for this V0 by Vi, so let me write it here. So the expression for V0 by Vi is obtained as V naught by Vi is equal to 1 divided by 1 minus j into 1 by 2 pi RC. I will write in the numerator divided by F. Correct? So this expression is rewritten here. So 1 divided by 1 minus j into 1 by 2 pi RC, I will bring to the numerator part here. So 1 by 2 pi RC divided by F, which can be modified or which can be represented as, which can be written as, this is equal to 1 divided by 1 minus j into FL. FL, I represent 1 by 2 pi RC as FL, which is a cutoff frequency value divided by F. Okay, so this is V naught by Vi. And what is this FL? From this FL is very clear. What is FL? FL is equal to, here FL is equal to 1 by 2 pi RC. And I call this as the cutoff frequency. I will tell you why it is called cutoff frequency, that we will explain very soon. So it is called the cutoff frequency. Okay, so the lower cutoff frequency of the high pass filter. Okay, we will soon, very soon we will prove that, we will see that below this FL, frequencies are highly attenuated, and above the this cutoff frequency, the signals are passed. Okay, so this FL is nothing but the cutoff frequency. It's called cutoff frequency. We will see why it is called a cutoff frequency, that we will see very soon. Okay, so anyway, the expression for V naught by Vi is obtained as V naught by Vi is equal to 1 by 1 minus j FL by F, where FL is 1 by 2 pi RC. Thus we obtained V naught by Vi as, the expression for V naught by Vi is V naught by Vi output by input is obtained as 1 by 1 minus j FL by F, where what is FL? FL is so called cutoff frequency, and that FL is equal to 1 by 2 pi RC. Okay, now let us analyze it more. Let us analyze this expression more. Okay, let us take the magnitude of this V naught by Vi. What is the magnitude of V naught by Vi? V naught by Vi, you take the magnitude, this becomes 1 by, what is the magnitude of A plus IB? I hope you know A plus IB, the magnitude is root of A square plus B square, right? So I apply this to the denominator part. So this becomes 1 by root of 1 plus FL by F the whole square. Okay, so the magnitude of V naught by Vi is equal to 1 by root of 1 plus FL by F the whole square. So let us see in detail about this magnitude or this absolute value of this V naught by Vi. Okay, let us see one by one. What happens at F is equal to 0? What happens at frequency? If frequency is equal to 0, let us see for a low frequency, let us see for a mid frequency, let us see what happens for high frequencies. Okay, let us see these three cases. At F is equal to 0, at frequency is equal to 0, what is V naught by Vi? V naught by Vi, magnitude of that, absolute value of that, this is equal to 1 by root of 1 plus FL by 0 the whole square, correct? So this is equal to 1 by root of 1 plus infinity. What is root of 1 plus infinity? Infinity. So it is 1 by infinity. This is equal to 0. So at F is equal to 0, V naught by Vi, the magnitude is 0. Okay, so F is equal to 0, V naught by Vi, the magnitude is 0. Similarly, what happens at F is equal to FL? Let us see what happens at F is equal to FL. What happens at F is equal to FL? Okay, so at F is equal to FL, V naught by Vi, magnitude of that is equal to 1 by root of 1 plus FL by FL, the whole square. FL and FL will cancel. So this becomes 1 by root of 1 plus 1 square, which is equal to 1 by root 2. 1 by root 2. So at f is equal to FL value, the magnitude I am getting V naught by Vi is 1 by root 2. So V naught is 1 by root 2 times Vi. At f is equal to 0, no output. At f is equal to FL, V naught is equal to 1 by root 2 times Vi. Correct? Now the third case is at f is equal to infinity case. What happens at f is equal to infinity? What happens to this magnitude of V naught by Vi? So magnitude of V naught by Vi is equal to 1 by root of 1 plus FL by infinity, the whole square. What is 1 by infinity? 1 by infinity is 0. So this is equal to 1 by root of 1 plus 0, that is equal to 1. Correct? So at high frequencies, at infinite frequency means very large frequency, high frequency. So at high frequencies, this magnitude of f V naught by Vi is equal to 1. So let me plot this. I'm going to plot this. Okay. So let me plot this here. So along y-axis, I will plot V naught by Vi magnitude of that. Along y-axis, V naught by Vi magnitude of that. And along x-axis, frequency. So this is called the frequency response, frequency cara. So let me plot, this is called the frequency cara. So I'm going to plot here the frequency cara. Okay, frequency cara means magnitude versus frequency, magnitude along y-axis and frequency along x-axis. Let us plot these three conditions. What happens at f is equal to 0? This is 0. F is equal to 0. At f is equal to 0, magnitude is 0 only. And what happens at this is 0 only. What happens at f is equal to FL? Let FL be here. Let this be FL. Let this be FL. At f is equal to FL, you will get somewhere, say, 1 by root 2. Okay, so you will get somewhere 1 by root 2. So it will increase like this and goes like this. Okay, so this is for FL. At f is equal to FL, the magnitude becomes 1 by root 2. And what happens if f is equal to infinity? Infinity means V naught by Vi is equal to 1. V naught by Vi is equal to 1. So if I plot these a magnitude of V naught by Vi for different values of frequencies, I will get a graph like this. So V naught by Vi versus f, I call it as a frequency cara. If I plot this, you will get something like this. So from the figure itself, it is clear, very clear, that here, see here, the high frequencies are passed here. High frequencies are passed and low frequencies are attenuated. Low frequencies are attenuated. Thus, high frequencies are passed and low frequencies are attenuated. So this is the frequency cara of a high pass filter. And this FL. See, this is FL. FL is that particular frequency at which the output is V naught by Vi magnitude is 1 by root 2 at FL. Correct? It is 1 by root 2. That means V naught is equal to 1 by root 2 times Vi. V naught is 1 by root 2 times Vi at FL. So hence I call it as, this is a cutoff frequency. Above cutoff frequency, almost all passed. Below cutoff frequency, very high attenuation. Okay. Hence FL is called the lower cutoff frequency. Lower cutoff frequency. FL is called the lower cutoff frequency. We will also represent FL with another name. See, what is 1 by root 2 in dB scale? So this is 1 by, this is a maximum value and this is 1 by root 2 times, right? What is this 1 by root 2? 1 by root 2 in dB scale. 1 by root 2 is, in normal scale, 1 by root 2. 1 by root 2 in normal scale. 1 by root 2 in normal scale. And this is equal to 20 log 1 by root 2. in dB scale, correct? 20 log 1 by root 2 in dB scale. And what is this 20 log 1 by root 2? If you solve, you will see that this is equal to minus 3 dB. Minus 3 dB. So that means in the normal scale, you will get the plot like this, where at FL value, if the maximum magnitude is 1, this is equal to 1 by root 2. In the dB scale, the same is equivalent to 3 dB. If I plot in the dB scale, this is 3 dB. So that means in log scale, at f is equal to FL, output V0 is equal to, output V0 is 3 dB below, correct, the maximum value. Correct? 3 dB below the maximum value. So at f is equal to FL. Typically at f is equal to FL. So at f is equal to FL, 1 by root 2 means 3 dB below. Hence it is called minus 3 dB cutoff frequency. So the other name is minus 3 dB cutoff frequency. Why it is called minus 3 dB cutoff frequency? So FL is also called minus 3 dB cutoff frequency, or just lower cutoff frequency, Okay. So why it is called minus 3 dB cutoff frequency? Why? Because in the log scale, if you take the magnitude of V0 by Vi, then you can see that there is a 3 dB difference. So that means output is minus 3 dB or 3 dB below the maximum value. Okay, 3 dB below the maximum value. Okay, hence it is called minus 3 dB cutoff frequency. Okay, so FL is denoted by different names, like either it can be written as minus 3 dB cutoff frequency, or it can be denoted as lower cutoff frequency.